This is some exercise for carbon-13 NMR. So first of all, again, C4H8O. What we have to do at the very beginning is to find the dBe, and the dBe for this case is equal to 1, right? Because we have 4 carbon and 8 hydrogen, no? So it's 1. So dBe1 equal to can be ring or double bond. And if you look at here, this area is 200 something. So if it is 200 something, comparing with hydrogen NMR, is divided by 20, is ended with about 10. So 10 is the aldehyde, right? So this carbon belongs to carbonyl. So we can be sure that this is the carbonyl group. Okay, and as you can see here, that it appeared as singlet, right? So if it is appeared as singlet, that means both sides of the carbonyl connected with carbon atoms. Okay, so we used already one carbon, and we know that it is ketone because we have only one oxygen, right? So it has to be carbonyl. Carbonyl with two sides can be just ketone or aldehyde because we don't have nitrogen or oxygen, right? So it have to be aldehyde or ketone. But this is singlet. This is ketone. Now, for the right hand side, we have two regions actually, about 20 to 40, about 30 something. Right? So if you divide it by 15 approximately, it ended with 2 ppm for proton NMR. Right? 2 ppm for proton NMR is the proton connecting with the carbon next to the carbonyl group. So that means these two carbon connecting with the carbonyl group, right? So we have C in green, we have C in maybe blue, right? So now we have blue carbon connecting with the carbonyl group, and then connecting with the green carbon. For green carbon, it is 2 hydrogen because it's triplet, right? So we know that this is CH2. But for blue carbon, it is quartet. So if it is quartet, this is CH3. And then we have, again, CH3 in pink color over here because it is quartet. So we have only one carbon left, right? So it's only one possibility. You have to put the CH3 pink color here on the left hand side. So this is it. So the molecule here is butanol. Okay, that's the first example. Okay, now we're going to look at the second question. Okay. For the second question, we have the molecule. We have signal carbon-13 NMR. It's carbon-13 NMR signal, and we have designed into A, B, C, D, E, F, G, right? So I give you the structure. So you have to put A, B, C, D, E, F, G, H here into the molecules. So I give you, you may pause here, and then after you try to find the position of signal related to the molecule, you can come back down to find the answer from me. Okay, so if you are ready, we are going to look at the signal right now. Oops. Okay, let's look at the molecule. We have 1, 2, 3, 4, 5 and 5, 6 and 6, and 7. So we have 7 types of 7 types of carbon, right? So with 7 types of carbon here, we can then relate with the signal. So first of all, let's look at the very unique structure carbonyl group. So we have one carbonyl group, and the carbonyl group normally appears at about 180 to 120. So we are quite sure that the C is over here. Okay? And then aromatic region, because we have 1, 2, 3, 4, 4 types of carbon, right? And we have 4 signal over here, D, E, F, and G, right? So D, E, F, and G over here are aromatic regions. And as we know that this one and this one are exactly the same. This one and this one are exactly the same. So the peak heights of these two signals have to be very, very tall. But only one carbon here and only one carbon here may be shorter. And again, as you know, C without H will be the shortest one, right? So the D have to be here and the G have to be here. So we have only E and F left, right? So E and F are very difficult to distinguish actually, because they are quite the same, right? But anyway, this is E, this is F. We can sometimes explain by the resonance structure as well, because this is oxygen, right? So it can resonate electron down here to the aromatic ring. And as you can see from the resonance structure over here, that the carbon E at the ortho position is partially negative, right? So it is clouded, it is shielded actually. So if it is shielded, it appears on the right hand side. So E and F comparing, E on the right and F on the left, because E is shielded by the electron from the resonance effect by the electron donating group of oxygen atom. Okay. Now we have A and B left. So B is here because B is next to carbonyl. For proton NMR, it have to appear at about 2 ppm. So you multiply with 15, it's ended with 30. And as you can see, B here is appeared at 30. So this is B and this is A. So that's it. Okay, now it's C5H8O2. Okay, you may pause here. What you have to do is propose the structure of the molecules using only this carbon-13 NMR. Okay. So after you finish, resume the video and we will see the answer. Okay, first of all, finding the dBe. And the dBe for this molecule is 2. So finding the dBe first, and the dBe of the molecule is equal to 2. And if the dBe equal to 2, it can be 2 ring, or 2 double bond, or 1 ring plus 1 double bond, right? So there are many possibilities here, 3 possibilities. But anyway, because we can see this signal, which is very important because it's 100 something, very far. So this is characteristic peak of carbonyl group. So you use 1 double bond already. So this is impossible, right? So the alternatives is are carbonyl with alkene to be 2 double bond, or carbonyl with the ring, right? So to find out whether this molecule is a ring or it is unsaturated carbonyl, you have to look at the sp2 carbon connecting with hydrogen atom, or alkene. The alkene normally appeared about 5 to 6 ppm for proton NMR. So if you multiply it with 20, it is ended with 100 to 120. So that's the position of alkene carbon. But as you can see over here, the position of alkene carbon is nothing here. So it has to be the ring. So this is cyclic carbonyl group. So cyclic carbonyl with 2 oxygen atom, there are 2 possibilities. Is cyclic ketone with hydroxy group, or cyclic ketone with ether, thing like that. Or another possibility is the cyclic ester. Because you have two O, right, two oxygen, it can be ester as well. So what else we can do? If you look at the splitting pattern, all of these are triplet, 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 and triplet. Everywhere are triplet. So you have only CH2, right, to be triplet. All of these are CH2. Right? So if you have only CH2, you have no CH3, you may quite sure that this is the ring. Because if it is open chain, you have the very end of the line, right? At the end of the line, it is CH3, but you have no CH3. So from this, you may be sure that it is the cyclic for sure. And at 70, if you divide it by 20, right, it would be 3.5 ppm for proton NMR. So 3.5 ppm for proton NMR is the proton NMR is the hydrogen connecting with carbon with very high En element, which is oxygen, right? So from this, that means this CH2 may connect with oxygen atom, okay, somehow connects with oxygen atom. So I may guess that this shall be like ester, connecting with CH2 in purple color over here. And then we have 3 of carbon left in the structure. So I think it should be green one, pink one, and yellow one. All of them are CH2 because you have only triplet over here, right? So it is CH2 in yellow color, it's CH2 in pink color, and it's CH2 green color over here. But where are they, right? First of all, if you look at the 30, right? The 30 over here is CH2, no? But normally for 30, if you divide it by 15 or 20, is ended about 2 ppm for hydrogen NMR. So this should be CH2 connected with the carbonyl, right? So the yellow color have to be this signal, right? So green and pink are here, first two signal, right? Green is about 2 atom to oxygen, but pink is about 2 atom to carbonyl. So I think green is shielded by the En of the oxygen atom better than the pink. So I guess that the green one is here and the pink one is here, and that's it. So we're going to look at the next example. So come to the last exercise for carbon-13 NMR. As you can see here, the following of resonance decoupled carbon NMR was obtained from a compound. You have the formula here, and C3H5Cl3, right, is trichloropropane for sure, because it is saturated because dBe equal to 0. So propose the structure for this compound. So you have to use the position and also the splitting pattern, right? So it is C3H5MCl. I zoom in a little bit like this. Okay, let's play. So you shall pause here, and then after you know the answer, come back again. Okay, now let's take a look at the answer for this question. So as you can see, we have quartet here. The quartet symbolizes CH3, right, indicating the CH3 in the molecule. We have 3 carbon. We have CH3 already. And then we have the pink color, CH, because this molecule, this position is doublet, so you have only one hydrogen atom connected to your carbon. And then in the yellow color over here is doublet again, so we have CH, right? But remember that we have 3 carbon, right? So we have to connect all these 3 carbon together, right? And there's only one possibility, right? They connected into a line. And so if I just start by CS3 in purple color over here, then the question is yellow or pink would be here, right? If I put the pink color over here, right? So if you don't know, you can just guess, right? Pink or yellow. So if you make a guess by put the pink over here, then the yellow have to be at the very end. And because the yellow and pink contain only one hydrogen atom, and the molecules contains 3 of the chlorine atoms, that means chlorine atoms have to be here, here, and here. And that's it. So as you can see, the carbon in yellow color contains 2 chlorine atoms. These 2 chlorine atoms are very high in En value, and then pull the electron clouds towards themselves. And then your carbon here is deshielded, right? Because you have less electron cloud, right? So this carbon interacts strongly with the external magnet. So you need higher energy level into in order to excite the carbon from gas state to excited state. So as you can see, the signal appeared at very far on the left hand, 75 ppm approximately. So this is the correct answer. Okay. So not only the structure of the molecules, you can also identify the signal, which signal belongs to which carbon in the structure, to confirm that your answer is correct. Okay. So this is all of the spectroscopic techniques that I want to summarize from your second year organic chemistry. So there are more of the exercise that is maybe you have to incorporate all the techniques together to find the answer, and I will show you some application of all the techniques as well. Okay, so see you again in the next video, and this is the end of the NMR spectroscopy. Thank you very much.